thermodynamics. So we gave two alternative statements and then proved that the two are equivalent. Violation of one implied violation of the other. After that, we defined something called a Carnot cycle. So the Carnot cycle physically would look something like this. And by definition, there are two isothermal processes. There's isothermal heat addition and isothermal heat rejection. Now, how can you have isothermal heat addition or heat rejection? Well, the simplest case is when a substance is undergoing phase change. The two isothermal processes are connected by two reversible adiabatic processes. So then if you want to plot this, one coordinate would obviously be temperature, so that the isothermal processes would be lines which are parallel, straight lines parallel to one of the coordinates. What about the reversible adiabatic process? Now, if we know how to plot that, and if we can find a coordinate where an adiabatic process would be a straight line, then the Carnot cycle would be a rectangle. So if you look up books, there is such a diagram given for the Carnot cycle, but then the adiabatic process is a straight line if one of the coordinates is entropy. And the problem is we have still not defined entropy, so we are still not in a position to draw this. But at least we know what the definition is, that there are two isothermal processes and two adiabatic processes. Now the natural question would be, okay, we were discussing second law of thermodynamics, then all of a sudden we introduce something called a Carnot cycle. How are the two related? So now let's try to bring out the connection. There are two properties which a Carnot cycle must satisfy, and the proof of those will come from the second law of thermodynamics. So we had also discussed that some processes are reversible and some are irreversible. So if it is reversible, you could just run it backwards. So whatever W transferred in one direction would be transferred in the opposite direction. Whatever Q transferred in one direction would be transferred in the opposite direction. So now it says that so having defined reversible processes, we then stated that the Carnot cycle consists of 4 reversible processes, and all these processes are reversible. So now proposition 1 says, so the first proposition says that if you have two reservoirs at two different temperatures and you operate engines which work in a cycle between these two reservoirs, then an engine operating between these can never be more efficient than a reversible cycle. So tacitly, it compares an irreversible with a reversible engine. So it says the irreversible, its efficiency can never exceed that of the reversible engine. So how do we know that this should hold? So then we try to use reasoning. Let us further assume that both of them, in both, the same amount QH is transferred from the high temperature reservoir to the engine during a cycle. Now I don't know whether the two have the same efficiency. Now the efficiency of a heat engine is the efficiency of anything is the useful output by the input which has to be provided in order to get that output. So energy sought is the work So considering examples, if you consider a motor car, what you would like to know is how much of um, driving power do you obtain? That is what is the useful output. Whereas, so how much brake horsepower you get from the engine, and the cost is how much of petrol you have to burn in order to get that. Similarly, for a power station, what is the electricity you generate divided by the cost of the amount of coal which you burn. So then it's always the W output compared to the QH. So it is QH which costs you money. The petrol provides the QH in a petrol engine. It's not a Carnot cycle, but whatever the cycle, the petrol is what provides the QH. Similarly, the coal provides the QH in a power station. So then the thermal efficiency is W by QH. W is QH minus QL divided by QH. Since we are discussing heat engine, we also stated that Carnot cycle, since each of the processes is reversible, the entire cycle is also reversible. So the entire cycle could be operated in reverse, in which case, so if you reverse everything, this QL will go from the temperature source to this. So it will extract QL from the low temperature source. So the low temperature serves as a source. Now, how is that possible? Because you have to put in, so unlike the engine where work was output, here you have to put in work as an input. So if you put in work as an input, then you can transfer QL from a lower temperature reservoir. So that is what it does. And since you have put in work, that amount of energy has gone in. QL has been drawn from the low temperature reservoir. That all goes to QH. So if you operate the entire Carnot cycle in reverse, you get what is called a reversed Carnot cycle, and that works as a refrigerator. So since we are discussing efficiency, let us also discuss the parameter which expresses how well a refrigerator is working. So it turns out that the parameter which we use often has a value more than 1, and we are not very comfortable talking of efficiencies more than 1. It seems to go against intuition. So then we don't use the word efficiency. Instead, we use the term coefficient of performance. So we use two different terms, refrigerator or heat pump. And the coefficient of performance will be different for the two. So how are the two different? In refrigeration, our intention is to remove Q from the low temperature reservoir. So we want to refrigerate a certain space. So then our useful output is how much Q we have been able to remove from the low temperature reservoir. On the other hand, thermodynamically it is seen that a heat pump is um, in a way better than a simple heater if you want to heat a space. So in colder climates, where during winter you would want to heat certain spaces, the idea has been around, though in practice, I believe it still isn't used, because uh, in most of the places where they have central heating, they still use a low-grade oil in a furnace to provide heating. But the idea is the heat pump could do it consuming less energy. So then, if you use the idea of a heat pump, what is sought is not QL, but adding QH to the space which you want to heat. So depending on whether it's a refrigerator or a heat pump, your useful output could be either QL if it's a refrigerator or QH if it's a heat pump. And what you have to put in, that is the work. So if it's a refrigerator, you connect it to the mains and it draws power. So that is what you pay for. So that is what costs you. And this is the useful output which you get, QL for a refrigerator, QH for a heat pump. So then and QH exceeds QL by an amount W. So this would be okay. So now we have defined what is efficiency of a heat engine. So what is more efficient that we now know? So then if the two, let us assume that the two have two different efficiencies. We don't know which is higher, we don't know which is lower, but all we know is the two could have two different efficiencies. So the efficiency of a heat engine would be W by QH. By assumption, we are operating the two engines in such a way that QH is the same for both. So then the W would be different for the two if the efficiencies are different. The W for the irreversible engine, if the efficiency is not the same, it must be different. But QH by assumption is same, so QL must be different. So we denote this by QL prime. So this is what the two engines look like. Now, let us assume that the irreversible engine has higher efficiency. Then with the same value of QH, if it has higher energy efficiency, it must have higher work output. That implies so QH I can cancel, and I can transfer the QL prime to this side and the QL to this side. So um, uh, um, what we have stated is that if there are two heat engines operating between two reservoirs, if we assume that the irreversible has a higher efficiency, it must be producing more work output. So then a larger fraction of this QH has been converted to work. So a smaller fraction of it would be rejected to the low temperature reservoir. So therefore this, since by assumption this has lower efficiency, uh, this smaller fraction is converted to work, and a larger fraction is rejected to the lower temperature reservoir as Q. So QL is greater than QL prime. Now this goes against the assumption of the first proposition. It says that the it is impossible to construct an engine that operates between two given reservoirs and is more efficient than a reversible engine. It says that an irreversible engine cannot be more efficient than a reversible engine. So we are trying to prove by contradiction that that is not possible. So we are assuming that, okay, let me assume that irreversible engine has higher efficiency. From this, can I show that it leads to some statement which we know is false? In that case, our assumption must have been wrong. So that is the line we are following. So if we assume that the irreversible engine can have higher efficiency, then QL must be greater than QL prime. Now, the reversible engine by definition can be reversed. So let's do that. Now I've reversed this. So QL plus QH minus QL, that adds up, gives you QH. Now we know if this has, by assumption, this has higher efficiency, so WIE is greater than WRE. Now that we have reversed it, this WIE is larger than this WRE. So let me tap an amount WRE from here. By assumption, this was more efficient, so WIE is larger. So the remaining part is this. In fact, that QL, all that property I need not have considered. We know that WIE minus WRE is positive. Okay, so maybe now it says, let us enclose this portion by a dotted line. So then, now I have included the irreversible, the reversed reversible, and the high temperature reservoir as my device. So it gives you a net work output, and okay, the what we proved probably helps here. which it would have followed either way from first law of thermodynamics, that if an engine is operating in a cycle and producing net work output, it must be absorbing Q from somewhere in order to satisfy the first law. So if I see the interaction with the low temperature reservoir, QL is going in this direction, QL prime is going in this direction. Now we had said that the reversible engine by assumption has lower efficiency, so less work output means more heat rejection to the lower temperature reservoir. So QL is greater than QL prime. So then the net transfer is in this way. So QL minus QL prime is what is transferred, and that is same as WIE minus WRE, follows from the first law. So now if you see, this is the device, again assuming that if both irreversible and reversible engine operate in a cycle, it means that this entire device works in a cycle. So this is a device which works in a cycle, and all it does is draw certain amount of Q, because QL minus QL prime is positive, so it draws certain amount of Q. So there's a certain amount of Q transferred from the reservoir to the engine, and all it does is produce work equivalent of that Q. Now that by second law, the Kelvin-Planck statement is impossible. So therefore, we started with the assumption that the irreversible engine has higher efficiency than the reversible engine, and then from that we using reasoning we find in that case we can construct a device which violates the Kelvin-Planck statement of the second law of thermodynamics. But evidence so far says that the second law of thermodynamics holds. So therefore, our assumption that the irreversible engine can have higher efficiency must be wrong. So therefore, the first proposition must be true, that if you have two reservoirs and you know the efficiency of a reversible engine operating between them, any other cycle cannot have an efficiency which is higher than that. So the efficiency of the reversible engine sets an upper limit to the efficiency of a device which works in a cycle and operates between those two temperature reservoirs. So that serves as the upper limit to the efficiency of such a device which works in a cycle between these two reservoirs.
Hello, sir.
Yes.
Sir, here QL minus QL dash cannot be equal to WIE minus WRE.
Why?
Sir, due to that Kelvin-Planck statement.
No, they are equal according to first law, but then it contradicts the second law of thermodynamics. So therefore, our right in the beginning, our first assumption must have been wrong.
Sir, to prove
So
this, that
by first law,
yes.
if there is a device, because QH is the same for both, and we have reversed one, in which case there's no interaction with no net heat transfer to this reservoir, to or from this reservoir. In that case, if I include this, then so this QH I could have transferred directly here. In which case I have only interaction with one reservoir and work output. So by first law, the two have to be equal. but it cannot be positive. So by our assumption, this quantity is positive. This cannot be positive because then it would violate the second law. So it's not inequality of these which solves the problem. We have to go right back to the initial assumption. That was an assumption. We said that, okay, let us assume that irreversible cycle can have higher efficiency.
Okay, sir.
All engines that operate in the Carnot cycle between two given constant temperature reservoirs have the same efficiency. So the proof is very similar to the proof for the first proposition. Whichever has higher efficiency, that you put in place of the irreversible engine and use the same argument, you'll again run into the same complication. So therefore, if you have two reversible engines operating between two reservoirs, they must have the same efficiency. Now, that tells us something nice, that the second law is a law which um, is concerned only with the temperature of the two reservoirs. So given two reservoirs at two different temperatures, it says, okay, the efficiency has to have a certain value. Now that is regardless of what is the operating fluid for your cycle. So then that tells us that using the second law, we can get a definition of temperature which is which has no dependence on any substance, which is independent of substance used for measurement of temperature. So if we can measure the efficiency of a Carnot cycle, of a reversible cycle between two reservoirs, that can be used to determine what is the temperature of the reservoir. So then, if we start with certain reference reservoirs, say one at ice point, one at steam point, then once we know that temperature, we can use the second law. So then, if we have a high temperature reservoir at a different temperature, if we measure its efficiency, that efficiency should provide us a value for the temperature of that reservoir. So let's say I have one at ice point, one at steam point. I operate a Carnot engine between these. That gives me a certain efficiency. Now I replace the steam point by a reservoir at a different temperature. I measure its efficiency. From the two efficiencies, if I can define what is the temperature of the reservoir with which I have replaced the reservoir at steam point, then the good point is that between that reservoir and the reservoir at ice point, the efficiency which I have measured, unlike the expansion varied from substance to substance, and that was what gave me different values of temperature depending on what material I use for the thermometer. Now here, the second law says, the second proposition which we discussed right now, that given two reservoirs, the efficiency of a reversible cycle operating between these two has can have only one value. So this is regardless of what substance you use. So then this can be used to define temperature. So let's say we have reservoirs at three different temperatures, T1, T2 and T3. And let's say this is heat engine A. It has work output WA. Now I operate engines A and B such that the heat rejected by engine A to Q2 is exactly equal to the heat transferred from the reservoir at T2 to heat engine B. Again, let me connect one more heat engine C And let's say Q1, which is transferred, the Q which is transferred from T1 to heat engine C is the same value as that transferred to engine A. So the heat transfer from reservoir at T1 to engine A and to engine C are the same, have the same value Q1. So I don't require any Q1 prime or anything. Now, this entire part I could consider as my heat engine, because the Q2 which is rejected by A is accepted by B. So I could do away with this reservoir and I could transfer it directly from engine A to engine B. So then engine A and engine B together would constitute a device. So that it takes Q1 from this reservoir at T1, and now this Q2 is just an intermediate. So finally, if I consider the entire device consisting of engine A and B, in that case, it would reject Q3 to reservoir T3. And Q1 minus Q3 would be the total work output from this device. Now we know, in order to define a temperature scale, we define a temperature scale in terms of efficiency of the heat of a reversible engine operating between these, because it's the reversible engine which has a unique value of efficiency if it is operating between reservoirs at two particular temperatures. So then all these engines are reversible cycles. So then the engine consisting of A and B, since both A and B are reversible, this entire device is also a reversible engine. So this is one reversible engine, and on the other hand, I could have a reversible engine directly working between T1 and T3 without going through T2. So then A plus B and C are both reversible engines operating between two reservoirs at temperatures T1 and T3. So by the second proposition, both of them must have the same efficiency. So if the heat transferred from the high temperature reservoir is the same, the work output must be the same, and therefore the heat rejected to the lower temperature reservoir also must be the same. So this must again be Q3. So in general, for a Carnot cycle, thermal, this is what it is by definition. W is equal to QH minus QL. Now this is a function only of the temperatures. So I can write this, that this is some arbitrary function which I do not know, let me call it psi of which means QL by QH so QL by QH is some function of TL by TH. So what is this function? That is what we are trying to figure out from here. So then, there must be some functional relation. We don't know what this function looks like, whether it is TL into TH or TL plus TH, or it is TL to the power TH. We do not know. It is some arbitrary function. That is all we know. Now, what it is, that is what we are trying to figure out. So whatever the function, the QL by QH is this arbitrary function of TL and TH, which we don't know what the function looks like. So we are trying to make out what that function looks like. Now, if I look at engine A, in that case, QL is Q2 and QH is Q1. And okay, so if I consider engine A, it took Q1 from reservoir at T1 and rejected Q2 to reservoir at T2. So then our QL is QL and TL are Q2 and T2, and QH and TH, the high temperature reservoir and the heat transfer from that, are Q1 and T1. So I can write Q2 by Q1 equal to psi of T2 by and T1. Similarly, if I consider engine B, so then I have again, if I consider engine C operating between T1 and T3, then I have Q3 by Q1 now Q2 by Q1 into Q3 by Q2 is equal to Q3 by Q1. The Q2s would cancel and you would get this. Now Q2 by Q1 is psi T2 T1 and Q3 by Q2 is psi T3 T2 and Q3 by Q1 is psi T3 T1. So this arbitrary function psi, which must be some particular functional relation involving the two temperatures. So the psi is some arbitrary function, but it must have certain form, how it depends on TL and TH. So it satisfies this. Now, if you observe, on the right hand side there is no dependence on T2, whereas on the left hand side you have a dependence on T2 in both of these. So somehow this dependence must cancel out when we multiply these two. Now, the final result, which the book states, we can easily see that it satisfies the property, but it doesn't really provide a proof that that is the only possible way. Now, in order to provide such a proof, you would probably have to look up books on functional equations. So those of you who have written the Mathematics Olympiad might be familiar with a subject called functional equations. There are books on it also. Now, most of us are not aware, most of us have never read that. So let's just state without a very rigorous proof that if the dependence on T2, so here it was psi of T2 by T1, here it was psi of T3 by T2. So when we multiply these two, it cancels out. Now that property would be satisfied if I had psi of TLTH is equal to function of TL by the same function of TH. If we assume that this function psi TLTH, which all we knew was it is a certain function, because that is what is required in order to satisfy proposition 2, that any reversible engine operating between two temperatures has the same efficiency, then it must be some function of these two temperatures. But now we find that in order to satisfy this condition, which we found follows from proposition 2, the psi must satisfy this. So if we assume that psi has this form, that psi of TL and TH is some function of TL by the same function of TH, then psi of T2 by, so let's substitute here. This would be function of T2 1. And this side would be function of T3 by function of T1. So if I assume this is in general valid for any TL and TH, then these functions I can these functions psi I can substitute in terms of f. So this is what I would have on the left hand side, and this is what I would have on the right hand side. So then we can see that if psi TL TH has this form, in that case it identically satisfies this law, which it should. So then people said, okay, let us take this as the definition of a temperature. Now, it would not provide a definition unless we specify what the form of the function is. So various possibilities are there. Kelvin suggested that let us take a linear dependence, that QL by QH which is your psi TL by TL and TH, psi as a function of TL and TH. Let us say that we have, so that is equal to psi TL TH, which we said is this. Let us say the function is a linear function. In that case, this provides a way of measuring temperature. So this was the definition of eta thermal. We had put from the definition of eta thermal, we had found that that is equal to 1 minus QL by QH. So that would be 1 minus TL by TH. Now people said, okay, fine. So now we can define a temperature scale, the thermodynamic absolute temperature scale. The thermodynamic temperature scale. So let us say we take our low temperature reservoir to be at ice point and our high temperature reservoir to be at steam point. So the assumption made is that these are reservoirs where water undergoes phase change from solid to liquid and liquid to vapor, and this is at atmospheric pressure. If the pressure were different, the temperatures would be different. So if we do this at atmospheric pressure, that we call the so by definition the ice point and steam point are where the phase transition occurs at atmospheric pressure. So if we do this, the efficiency, if we can measure, but the book says in case we could measure, so it seems it's not easy to measure. But if you can measure, then the efficiency turns out to be this. So from this, we know the value of TL by TH. It still doesn't give us a unique value of for TL or TH. So then we need something more. So that something more we define to be the um, um, interval. So we define it to be the scale for the temperature. So we arbitrarily assume we could take we could measure lengths in terms of centimeters or in terms of inches. Now both give you measurements of length, but the inch is a longer unit of distance, longer unit of length compared to the centimeter. So then both are equally valid. So you could choose one or the other. So then we need to choose how large a difference means 1 unit. So an arbitrary assumption which is made is that, let us say, the interval between the steam point and the ice point is 100 units. Now, the fact that the second law could be used for defining a temperature, this was pointed out by Lord Kelvin. So in his honor, this temperature scale is called the Kelvin scale. So if we assume that the steam point and ice point are separated by 100 Kelvin, then this together with this would give us unambiguous values for both the ice point and the steam point. So from here, that means T of so I've used the fact that steam point is 100K more than the ice point. So from this, I can say steam point is T ice point plus 100K. So that is what I have put here. Now let me take the reciprocal. Then I would have 1 plus so from this, the final result which the book says is, but if you use this value and calculate, you'll get 273.13, which means not that this value is wrong, but that this value given in the book is not accurate. So it should have been given with higher accuracy. So when it's given with proper accuracy, what you get is this. And if this is 273.14, so this is how the thermodynamic scale is, temperature scale is defined. Okay, now I've overshot because I wanted to complete this point. So typically I give you a 5-minute break, and the 5-minute break is all the more important today because this gives me a free time to discuss about the class test. So the first question was, what would be the syllabus? So I had already, so I had told you that whatever I teach till today will be the syllabus. Now I have started teaching second law of thermodynamics. So what is the portion of second law of thermodynamics which would be included? And then the more serious question which you would have, that for the first law, you asked me which are the chapters from which you have to work out the problems. Now, second law, we are still midway in the discussion. So unless we complete the discussion, it's difficult to start working out problems. So then what do we need to do as far as the second law is concerned in order to prepare for the class test, which is next Friday? So there I would clarify that any question on the second law would be a conceptual question rather than a numerical problem. So if you are thorough in the concepts, even if you have not worked out any problem, you should be in a position to answer the question which would be posed. Next point would be how long will the test be? So there I asked this, I posed this question to the academic section, and they said that whatever decision was taken 1 year back still holds. So that decision the guidelines were circulated, it says that the class test should be of at least around 1 hour. So then what I would do instead, if I want to take a 1 hour test, I would have to give you, normally we give you 5 minutes extra in order to read the question. So if an exam starts at 9 o'clock, that is what say exams, how exams used to be held. So if an exam starts at 9 o'clock, in that case, the question papers used to be distributed 5 minutes early, so that by 9 everybody gets a question paper. So in this case, since you have to upload answers, and I told you the final answers would have to be just the final numerical answers would have to be uploaded within the time limit, and the detailed answer script scanned copy would have to be uploaded after 10 minutes. So what is the format for the answer, etc. So all those instructions are contained in the question paper. Now since this is something new, and since no clear guidelines have been provided, it is left to the teacher. I presume every teacher has his own way of handling it. So you need to read the instructions and submit your final answers accordingly. So therefore, I'll give you another 5 minutes in order to read the instructions. So I'll require 10 minutes there. And in order to upload and send me the scanned copy, I'll give you another 10 minutes. So we require another 20 minutes. Our class is of duration 1 hour 55 minutes. So if I deduct the 5 minute break in between, we get 1 hour and 50 minutes. So if I deduct the 20 minutes, the 10 minutes in the beginning and the 10 minutes at the end, we would be left with 1 hour and 30 minutes. So this Friday, I'll hold a test of duration 1 hour and 30 minutes. So I've already told you which are the two chapters from which you have to work out the problems. So these are the two chapters on first law of thermodynamics and first law applied to a control volume. And the added problem is most teachers have been complaining that since the students are writing the exams from home, it is very difficult to have the same level of rigor that we had when we conducted the exams using paper and pencil, using paper and pen, where the students would come to an exam hall and write. So that is where the problem which many people are facing, that most students seem to be getting more or less the same marks. So in order to avoid that, I'm trying two different, trying to introduce two differences. The first difference is that the numbers would be different for different students. This I've already told you. So the final answers also would be different for different students. The second point is, in order to bring out a difference, what I've always believed, that if everybody gets the same score, in that case it is being very unfair to the good student, to the student who studied seriously, if he gets the same marks as everybody else. So therefore, apart from answers being different, we should also make sure that the exam also brings out the difference in level of understanding and the necessary hard work put in. We must ensure that this is brought out in the scores, which is becoming difficult in this online mode. So then I'm saying this because when you practice problems from a book, uh, my observation is in most of these textbooks, typically we follow American textbooks, there are a large number of problems, most of which involve just plugging in values. Only a few of them are require a little bit of thinking. But then, if we are to test how much a student understands, we must pose questions which would require a bit of thinking. So giving it all of a sudden without sufficient warning would not be fair. So that is why I'm saying this in advance, that be prepared that at least one or two questions would be a little difficult. But if your understanding is good, you should be able to handle it. So prepare accordingly, that at least one or two problems may be difficult. So that is about the exams. If you have any questions about the exams, you can ask.
Sir,
Yes.
so from second law of thermodynamics, only concept-based question will come.
Only concept based, because you are not getting time to work out problems.
Yes, sir. Okay.
And sir, test will be conducted through Moodle only, no?
No, it will not be through Moodle. I don't know what Moodle permits, because I am doing it in the conventional manner. So in the conventional manner, we never used this multiple choice questions. What you have, and actually Moodle also has a problem that the Moodle server, it has to be submitted to a server in the institute. Those servers often are not able to handle the load. So Moodle getting into problems has been a problem in the past. So what I'll do instead, that I have a separate, I created a separate Gmail account specifically for these, for the online teaching. The reason that I did it is that institute, now that everything is online, there are various sorts of emails. Everybody who wants there are a lot of people who think that, okay, this is something which the entire IIT community needs to know. So that involves a variety of things. The authorities tell us about the rules and procedures. Then there's somebody telling you about availability of vaccines. Then there are those people who are selling instruments. They are going through a really bad time because nobody wants to buy instruments today. So they send emails with pictures of the instruments which they want to sell. The consequence of all this is our account gets overloaded. So there's always a risk that the emails might bounce. So in order not to add to that load, I made a separate Gmail account. So what you'll have to do is, within the time limit, you'll have to send an email containing the final answers. And within the next 10 minutes after the deadline is over, you'll have to submit a a JPG or a PDF file which contains the scan of your entire long answer script. So therefore, when you come for the exams next Friday, come with sufficient blank paper, enough for 1.5 hours of writing, because this will have to be scanned and sent to me at the end. So is it clear now? So you will come with paper and pen ready. You will log into this MS Teams. And what I would additionally require, this is something which the authorities have been telling us, that there should be invigilation. So therefore, you'll have to have a camera on during the entire exam. Okay. So you'll log into this MS Teams, have a camera on. I'll send you the question paper through email. So then there'll be a set of question papers, and I'll give you a list which question paper is for which roll number. So accordingly, you'll pick up the question paper which is meant for you, and that question paper will have your roll number and name on the first page. So once you have downloaded that question paper, just confirm that your roll number and name are there on that question paper. So each PDF file will have on the first page a roll number and a name. So all these roll numbers and name are there in a file. So the software picks up this from a file. So just as it puts different numbers inside the question, it also puts your roll number and name on the first page. So check that, then you know it's the right question paper. So take that question paper and write down the way you write down a conventional paper. So within the time limit, whatever answers are to be uploaded, that will be mentioned in the question. So those final answers, typically I say, when I say upload this, I give the unit also. So it has to be in that unit. So once the unit is specified, all you have to upload is a number. And don't use too much of approximation, because typically what we say is around 4 significant figures should be maintained, because the numbers are different for different people. So then the answers are different for different people. So then in order to be sure that you have got the correct answer, which is the appropriate answer for your value of those parameters, it's important that you maintain certain amount of accuracy. So finally, again, you'll have to have some arrangement for scanning. So it could be a scanner, it could be just using your camera on a cell phone. So you'll have to send me the scanned answer script as an attachment. Okay, so this is the mode in which the exam will be held.
So how do we send the final answers to you? We type it and send it as an email?
Yes, the final answer you type it and send it as an email, and the full answer script, that would be sent as an attachment, again as an email.
Okay, okay, sir.
And I'll also specify the name of the file, so that because earlier I used to do it with the smaller class, but this time the class is larger, 81 students. So if the file name contains right in the beginning the roll number, in that case sorting it becomes easy. So that I'll specify.
Sir,
So
so is it not like a Google form submission? Like you give the question Google form and we'll just upload our answer script in the Google form or something.
no, because I'm not sending you one question paper, I'm sending you 81 question papers. And there'll be a difference in the numbers, in some of the numbers, from one question paper to the other. Because this is okay. So I have a software. So I have to first generate those set of numbers for the 81 students, and then I have a software which generates the the question paper. So the question paper, the text will be common, but these numbers will be different. So that has to be done by a software. And then I have a software which generates final answers. I can also have a software which generates the full answer. So then now what I again do, one of the reasons for asking you to submit the full answer script is, in the past I have found that one small error somewhere in the beginning can result in all your answers being wrong. So if I base my evaluation only on the final answers, then that student gets a 0. But in the past, when I asked them to submit the full answer script, I could then go back and take a look, why are all the answers wrong? So then I could identify that, okay, this one step was wrong, because of which all the answers ended up being wrong. In that case, I deduct marks only for that mistake rather than for all the answers. So that is why for safeguard, I asked for the scanned copy of the full answers paper. So if I have to do this, I probably have to, I mean, I'm not very comfortable reading, say 81 students, and if you write around 10 pages in a 1.5 hour exam, so 810 pages, I definitely wouldn't like to see it on screen, so I may print it out. So then those printed out answers tell me exactly what you have done. So the answers will be different. So that is why a special way is required in order to do this. Now Moodle does this, Moodle allows for this, but that is only for short questions, I think. This is a long question. Typically you have, so this 1.5 hour exam will probably have 3 questions, and the 3 questions may not be of same weightage. So there may be one difficult question which may have twice the weightage of the 2 simpler questions. So each question, the answer may be fairly lengthy. So it is just like a conventional, something like your board exams. So proper evaluation rather than student friendliness is the priority. I hope that is acceptable. Okay. So also keep in mind that at least one or two of the questions will be difficult.
Hello, sir.
Yes.
Sir, will there be a compensatory test? Compensatory
Compensation for what?
for this exam?
No, I mean, all the tests will be difficult. So you can't escape that way. And actually, if the level of difficulty of different tests is different, first thing, now that you're writing from home, there should not be any reason for absence. In the past, when I used to hold exams in the conventional manner, that time also, if a student misses an exam, is able to properly justify why he was absent, say he has fallen ill, seriously ill, he was hospitalized, in that case, I would take that as a valid ground. But when I compensated for that, then I would compensate from his scores in other exams, but then I would multiply by a factor. The factor would be the score in this exam of the other students by the score in the exam for which I am taking your score of the other students. So I would take a factor which expresses the level of scoring in this exam compared to other exams. So that I would take from the rest of the class and multiply by that factor. So if you miss a difficult exam and say I'll appear in the easy exam, even if you give me a valid reason, the factor would take into account the level of difficulty, and therefore you would not have an advantage. So the tricks, just as students have tricks in order to try to increase their score, we also have our tricks in order to undo all those schemes. So so those methods are not going to help you. And since you're writing from home, you have to write every exam. So apart from these three, we also have to take a few quizzes because that accounts for the remaining 40% of the weightage. So for that, I'll take a few short quizzes. So maybe there'll be 4 quizzes together with these 3 tests. So that should provide a sort of reasonable assessment of your understanding of the subject. And level of difficulty, I'll always maintain a certain level of difficulty so that it brings out the difference between a student who has understood the subject well and a student who has not.
Sir,
Yes.
the number of tests you're conducting, is there like some best 2 out of 3 for evaluation or something?
No, there is no such thing. The
Sir,
notice issued by the institute makes it clear that 3 exams would be minimum of 3 exams have to be conducted, and this time they have given the schedule also. These are the weeks when you should conduct exams, and students are required to sit for all 3. No,
sir,
I think that,
and the
so when
and
these questions will be difficult, I think you should take a straightforward attitude and study well. That is the simplest solution instead of trying all these schemes.
sir, and what are the quizzes, sir? Like
Quizzes would be more like conceptual questions because the time is limited. Huh. In fact, all these instructions earlier, when I had a class which was somewhere near the end of the day, I could continue for some time and give all these instructions. But now it seems that a lot is being written that the online time there should be some limits to it. So even these class tests and all we used to take outside class hours, but now the institute says that these have to be within the timetable. So therefore, all these instructions took up more than half an hour. So we are losing time. So therefore, time is limited. So within that, I have to see how I can accommodate those quizzes. So it has to be short so that it doesn't take up too much time. I'm only saying this because from some of the questions which were asked in the last class, I seem to get the impression that some students think, okay, if I can work out all the problems in Van Wijlen and Sontag, that's all I need to do. If I'm able to work out all those problems, I can score full marks in this test, no questions asked. I just wanted to caution you that it may not be as simple as that. Just keep that in mind. Okay, now that we have any more questions? Okay, now that we have a temperature scale, so this temperature scale came from one assumption. All we had shown was that QL by QH should be f of TL by f of TH, and then all of a sudden we said let us assume that this f of TL is simply TL. Now it seems this is not the only choice. If you look up Van Wijlen and Sontag, you will find that Kelvin had also suggested an exponential dependence. So then the question would arise that with a certain assumption about the functional form of this F, we define what is temperature. So how does this temperature tally with the the temperature scale which was based on
triple M.
pardon? Okay, earlier we used to take the expansion as a measure of temperature. So the thermal expansion was used to measure temperature. Now that it was found was giving a scale which gave you different values of temperature with different choice of the material whose expansion was measured. So then people said, okay, let's try out different ways. So then they said, okay, another way where you don't use expansion, let us use the fact that at a constant volume, the pressure of a gas is of an ideal gas is proportional to temperature. So people said, okay, let's say I have a bulb. I say I allow the mercury column to come up to a certain mark. So then the volume remains constant. As I change the temperature, the pressure goes up. Accordingly, I add more of mercury to balance the pressure. So depending on what the temperature is, in order to bring this meniscus to this level, I'll have to add varying amounts of mercury. If I increase the temperature here, I'll have to provide more of mercury here in order to bring the meniscus to this level. So that this pressure matches this pressure. And this pressure, since it's at constant volume, it is proportional to temperature if it is an ideal gas. But as I said, ideal. Gases are not ideal. So what happens if it's a real gas? If it's a real gas, then the pressure measured would be different for different gases. But then it was observed that as the deviation from ideal behavior increases as the gases become more dense. As they become more rarefied, they tend to approach towards the ideal gas behavior. So then what people said, if I take temperature measurements and I do this experiment for different values of pressure. So this whole equipment I could enclose in a sealed chamber and do it at different pressures. So then for the same temperature, if I carry out the measurement at different values of pressure, then I'll get different values of temperature. Now let me extrapolate the graph and find what is the temperature, what is the extrapolated temperature at zero pressure. So when they did that, they found that the extrapolated value at zero pressure turns out to be the same for all gases. So that was defined as the ideal gas temperature. Now, the question would arise that this Kelvin scale, which came after we made this assumption, how does it relate with the ideal gas temperature? Are they at all similar, or is there again a dependence? Say it may turn out that the thermodynamic temperature scale is proportional to logarithm or to the tan hyperbolic of the absolute gas scale. How do we know that the relation is not something complicated? Are they the same or are they different? So then this part I'll leave as an exercise to you, that what the argument is. So what is a ideal gas Carnot cycle? What if an ideal gas is made to undergo isothermal heat addition and adiabatic change of temperature, just the way the Carnot cycle specifies? So I could in principle do that. If I do that, and using the ideal gas law, I calculate the efficiency of the Carnot cycle. So then that can be plotted on a PV diagram. PV because these are quantities which I know what they are. So the isothermal lines are something like this. So if temperature is constant, PV has to be constant. So as P decreases, V increases. So okay, so as P increases, V decreases. Now we have to also plot the adiabatic lines. So then between an isothermal and an adiabatic, so how do the two graphs look like? This is V. Let's say so then if I consider the expansion, so let us say I have a gas at a certain pressure and volume. I now move the piston outwards so that the volume increases. So typically, if I were doing it at constant, yeah. Okay. Now, if I keep this at constant temperature, in that case, the piston is moving outwards. The gas is exerting certain amount of pressure on the piston. So the gas is doing certain amount of work on the piston. So therefore, W has a certain positive value. Now, the gas is kept at constant temperature. Now, for an ideal gas, the internal energy depends only on the temperature. It need not necessarily be a linear function, but it has to be a function of temperature only. So if I'm not changing the temperature, the internal energy does not change. So then, if I have to keep it, so if I have to do certain work, since there's no change in internal energy, I must supply a certain amount of Q in order to compensate for that work. So to keep the expansion isothermal, I have to supply a certain amount of Q. So if I do not supply that Q, in that case, I expect that the temperature will drop. So the internal energy provides energy for the work done. So the internal energy drops and consequently the temperature drops. So if I expand through the same difference in volume, the temperature for the adiabatic expansion, the final temperature would be lower. For the same volume, if temperature is lower, the pressure must be lower. So then the adiabatic would look something like this. So therefore, the adiabatics would be something like this. So then, on the PV diagram, I could have an ideal gas Carnot cycle, something like this. So this is discussed in Van Wylen and Sontag. I'll leave it as an exercise to you to read up this. So sometime during those surprise quizzes, I'll ask you this question. So therefore, don't just ignore it, read it up. So there it shows that each of these processes is a well-defined process, and we know the working fluid satisfies the ideal gas laws. So what is the W, what is the Q for each of these processes, we can calculate. So when we do that, it turns out that the efficiency of this cycle so therefore the and you have QL by QH is equal to TL by TH. So from thermodynamics, all we knew was QL by QH was some function of TL by some function of TH. But if we say that our Carnot efficiency, so if we assume that QL by QH is TL by TH, then the Carnot efficiency turns out to be this. Now, if I assume the TL and TH as defined from the gas laws, so that is the temperature which you would observe from the ideal gas thermometer. So that ideal gas thermometer, that gives you a Carnot efficiency for the ideal gas Carnot cycle to be this. So therefore, our assumption that the Carnot efficiency is 1 minus TL by TH agrees with the ideal gas Carnot cycle, and therefore the ideal gas temperature and the ideal gas thermometer and the absolute temperature scale give you the same value of temperature. So the equivalence of the ideal gas temperature to the thermodynamic temperature scale, that is explained in Van Wylen and Sontag. So that I'll leave as an exercise to you to read up. And okay, we have only 3 minutes more. So the next topic I'll continue in the next class. So these 3 minutes, if you have any questions, you can ask. In fact, since the next it's lunchtime after that, so up to 1 o'clock it's available. Okay, so if you don't have any questions, we'll stop here. Guten Appetit.